infinity categories.
Okay, so thank you very much. So I'd like to start today. So I would like to, in a little while, I'll get back to finishing what I was saying at the end of Friday about that example. But first, I'd like to start with sort of today's slogan, you might say. So let's just write infinity categories here. And so you might say the slogan to start off today is that fibration over a space is the same thing, is say supposed to be the same thing, as a representation, well, let's say an action of what's called the Poincare infinity groupoid. So let's write this pi infinity of x. So let me try to explain this, and this is going to help us unwind the end of the discussion on Friday afternoon. So to explain this, let's just recall the case that everybody knows about, which is that a covering space y into x is the same thing as an action of the Poincare one groupoid. And by an action, I mean a functor from this pi 1 of x into sets. Okay, so let's recall what's pi 1 of x. So pi 1 of x is capital pi 1 of x. So it's the groupoid version of the fundamental group of x. But remember, the fundamental group of x, you have to choose a base point. Here we didn't choose a base point. So this is the groupoid. With ob. Pi 1 of x is just equal to x. Well, we might call that x discrete. So this is x as a discrete set. And more pi 1 of x from one point to another is just homotopy classes of paths from x to y. Okay. So I think, as you all know, this is a functor from this groupoid to sets is the same thing as a covering space. So if we have a covering space y, that's going to correspond to the functor f from this pi 1 of x into sets, where you just say f of the object x equals the fiber y index x. So if we call this let's call this f. This is just f inverse of x. So in this setting, in the case of a covering space, then by a covering space, I mean. In the case of a covering space, the fiber over any point is a finite set. And when you move along a path, you have an isomorphism of finite sets. So of course, the number of points in the fiber is the same for any point in the same connected component of x. Okay. So now our slogan for this morning, we would like to sort of soup this up this classical fact. So, remember, this is really what's underlying like all of étale cohomology and stuff like that, because Grothendieck said, okay, to define some kind of fundamental group or fundamental groupoid of an algebraic variety in characteristic P, let's just use this notion of covering and sort of go backwards and get back to the pi1 of x. Okay, so this is a fundamental concept. So now we would like to soup this up to have a pi infinity of x. So pi infinity of x is supposed to be something. It's supposed to be a category enriched over spaces, sort of like, let's call it a spatially enriched category. And this concept of spatially enriched category, this is really what we mean by infinity category. So it's supposed to be a spatially enriched category. Now, what does it mean to have a spatially enriched category? The objects are still going to be a set. It's still the set x delta, the discrete set of points of x. But now, more in this category, from a point x to a point y, what's it going to be? Well, so we want to, yeah, the idea here is that when we did this, we truncated down something when we said homotopy classes of paths. So it said two paths, if they're homotopic, they're the same element, but if they're homotopic in several different ways, we're not going to care about which way that was. Okay. So, so the idea here is just to forget about that squishing down stuff. And let's just say this is the space of paths from x to y. So it's, let's call this pxy. Okay. In x. So now you might say the question is, how do we give this a nice structure? And so you might say the composition of paths is supposed to be concatenation of paths. But if you think about it, concatenation of paths is not associative up to the nose, on the nose. Now, let me point out that if x is connected, then all the objects are going to be equivalent in this groupoid. So and so this category, is basically the same thing as just P of xx, but considered as some kind of group object. So if you have a groupoid, then if it's connected, then that's the same data as just choose one of the objects and look at the group, the automorphism group of that object. And this is just the loop space of x. So this question falls under what the topologists call the question of de-looping. So our question So what's de-looping? So de-looping means, okay, suppose we knew the loop space of a space, and we would like to recover what the space was. In other words, what's the extra structure on the loop space that needs to be put in so that we could recover the space? So in other words, what is So that's the de-looping question. And so the topologists developed a lot of stuff called what are called de-looping machines. So a de-looping machine is a way of talking about that structure. So kind of a first step is like an H space. But what's an H space? An H space is just a group object in the homotopy category. But this is not enough. So this is early on recognized not to be enough. So I guess I don't have the examples on the top of my head here, but there are going to be things like H spaces, so a group object in this homotopy category, which don't lift to a de-looping structure. And there's going to be cases where, given the H space structure, there might be several different ways of having it have a de-looping structure. So that's just not enough information. But so, okay, there's lots of different ways of doing that. But so the one which is actually interesting for us today is Siegel's de-looping machine. So Siegel really gave what I feel is a very elegant solution to this question. So to understand this, let's just go back to this problem of defining this infinity groupoid. Okay. So the idea is that we can define this P thing. So P, which is P depending on X, the sort of the loop groupoid, you might say. As follows. So for any n, let Pn be the space of maps. Let's delta n is the set of points, T0, Tn in R n plus 1, such that Ti are positive and the sum of Ti equals 1. That's just the real n simplex, okay? And Pn is going to be the space of maps from delta n into X, discretized on the vertices. So more precisely, Pn is Hom, let's say maps from delta n into X cross over maps from the set of vertices, so let's call that 0 up to n. There's n plus 1 vertices of the simplex X. So these are spaces. So this is the space of maps. This is, actual topological spaces. This is the space of maps. This is the space of maps on the vertices. And this is the discretized set of points to the n plus 1. Okay? So this is maps from 0, n into x delta. So that's what I mean by discretized on the vertices. So it means that when you're varying a continuous family of points inside here is always supposed to have the same vertices. Okay? It's a continuous family of maps from the simplex into x, but which the vertices are supposed to stay constant. So, for example, Pn is a disjoint union over all sequences of points in x of what you might call Pn of x0, xn. And this thing is equal to maps, let's call it maps x0, xn from delta n into x. Okay, so does everybody see? So this is the space of maps from the simplex into x, which fix the vertices at the points x0 to xn. And then Pn is just a disjoint union of those spaces. That's what this discretized thing means. So let's see what happens for n equals 1. So for n equals 1, P1 is the disjoint union of P of xy and P of xy is maps from 0, 1, I mean that's the simplex, into x, which send 0 goes to x and 1 goes to y. Okay? And this is just paths in x from x to y. Okay? So the P1 is just the disjoint union of the space of paths. But P2, it's bigger than some kind of just product of spaces of paths because it's a space of actual maps from a 2 simplex into x. Well, so what's Siegel's observation? So the first observation is that these things are organized naturally into a simplicial space. So let's write it here. And so on. So let me not write that down, but that's kind of easy to see. You just, the face maps and the degeneracy maps are just obtained by applying the face maps and the degeneracy maps on the simplex. Okay? But so for example, from here to here, remember this is the disjoint union of P of xy, and this is just x discrete. This is just a set of points of x, and the two different maps send P of xy to x and to y. Okay? And the map going the opposite direction is that sends a point to the constant path at that point. That's A. But B is that the simplicial space has a nice property. That's called the Siegel condition. What does the Siegel condition say? It says that if we take Pn, we can map it to P1 we can map Pn into a fiber product of copies of P1. Okay? So it's really Pn of x0, comma xn really goes to P1 of x0, x1, cross, and so on. This fiber product over P0, remember P0 is a discretized space X. This fiber product over P0, this is an easy fiber product to do because this is not a space, it's just a discrete set. And it just means that these things are disjoint unions of things. and we just take the product. So it says that the x1 here has to be the x2, has to be the second one here has to be the first one here. So px0 x1 cross p of x1 x2 and so on. Okay. So that's the Siegel condition. Now, why is that true? That's true because the simplex retracts onto the spine. Okay? Delta n retracts onto its spine. Sorry, thank you. This is an equivalent. It's a weak homotopy equivalence. So it says that this is a weak homotopy equivalence between this guy and this guy. I mean, I guess it's probably given enough hypotheses. I mean, it's probably a strong homotopy equivalence, but anyway. This just says that delta n retracts onto its spine, which is just a union of intervals. Okay? So, for example, a triangle is going to retract onto that. That's not me, right? Yeah. A tetrahedron is going to retract onto just this thing. But just pretty much any way you want, just sort of squish the extra stuff over to the spine, and that's relative to the vertices, fixing the vertices. So this is kind of the main point as to what's going on, why this is working, right? So in homotopy, the relative space, a simplex relative to its n plus 1 vertices, is the same thing as just an interval relative to n plus 1 points. Or that would be the same. Any contractible space with n plus 1 distinct points in it is going to work perfectly well. I guess there's a point about ordering things here, but okay. So that's B. And let's comment that this is really a generalization of the classical property of the nerve of a category. So this is a generalization of the classical characterization of a nerve of a category. Classical. A simplicial set, let's call this maybe A dot or something like that. Of course, if you have a simplicial set, then property A is, property A is automatic. Maybe I should just wanted to just write down kind of an A prime here, which is that that P0 is a discrete set. This is the thing which can be relaxed in more advanced settings. The what's on the nose? No, it's not at all an isomorphism. This thing is maps from the spine into X. And this thing is maps from the simplex into X. So there's lots of ways you can sort of wiggle around the rest of the question is how are you going to fill in this part? But the point is that's contractible. Yeah, but thanks for the question. That's exactly the whole point of this whole situation here. Of course, when we're doing a simplicial set, of course, then there's no choice. I mean, weak homotopy equivalence is just an isomorphism of sets. Okay? And so this is the classical characterization of the nerve of a category. It's the same thing as a simplicial set, which satisfies this condition, that that's an equivalent, that that's an isomorphism. For a set considered as a space, weak homotopy equivalence is the same thing as isomorphism. That's the definition, you might say. Now then there's going to be condition C. let me just write condition C in kind of the easy way to write it. So condition C is a sort of a group-like condition. Which we can write, I'll need to explain this at some point, or you can kind of imagine what it means, but which is that the tau less than or equal to 1 of the p dot, which is a category, which is kind of automatically a category, maybe I could say what this is. So tau less than or equal to 1, tau less than or equal to 1. So tau less than or equal to 1 of p dot is the category whose nerve is the simplicial set n maps to pi 0 of p dot, pn. Okay. So if we apply pi 0 to something, to which is a weak homotopy equivalence, it becomes an isomorphism of sets. That's part of the definition of weak homotopy equivalence. And pi 0 also is going to commute with this type of homotopy fiber product, using the fact that these p zeros are already sets. Pi 0 is not really going to commute with a fiber product in general, but like a homotopy fiber product. But if it's fiber product over sets, then pi 0 of the product is going to be the product of the pi zeros. Okay, so if we just apply the functor pi 0 to our spaces, we're going to get a simplicial set whose n simplices are this thing. And that defines a category by exactly this observation. And the condition of C is that this thing, which is automatically a category, is in fact a groupoid. So C basically says that maps, arrows are invertible up to homotopy. Okay. So that's Siegel's delooping machine. So what does the machine say? Well, it says, well, what Siegel really said, and I actually even asked him about this, and he didn't really have an answer, but which is why they didn't go to the case of many objects, why they were sticking to the case of a single object. But I mean, it doesn't really matter for a connected space. But so what does Siegel say? Says that this structure, so the structure of a simplicial space satisfying conditions B and C. And so Siegel kind of added the condition, what you might call A double prime, which is that P0 is equal to just 1 point. So as you can see, this is going to be perfectly sufficient for dealing with connected spaces, because we can always just choose a base point. We can just look at the sub-object of this thing, which is everybody which maps only to that 1 point in P0, okay, by all the maps. Okay. The structure of simplicial space satisfying B and C and this A double prime is a delooping machine. Let me not write down a big paragraph about what that means, but what does it mean? It means that if we have one of those, then we can deloop and get a space, and if we apply this construction to that space, we're going to get back to something which is equivalent to the one we started with, and in the opposite direction. So you might say, what's the realization of P dot? This is just the realization of the simplicial space. Let's say So if we think of the simplicial space as a bisimplicial set, this could just be the diagonal simplicial set. But there's a whole discussion which I don't really understand very well there's a whole discussion of different types of choices of realization. There's like the fat realization and whatever. There's different ways of realizing a simplicial space. Part of the problem being that if you really wanted to do a simplicial object in the category of topological spaces, then you would have to be careful about cofibrancy kind of conditions and stuff like that. If we say, as we're doing here, so this is a general convention here, is that when I write the word space, I really mean a simplicial set. But that's a simplicial set in a different sense than this is a simplicial set. I mean, this is a simplicial set where the simplicial direction is really providing some kind of specific kind of structure. Of course, they're related, obviously, but by space just means some kind of combinatorial realization of a space into simplices, into pieces. So that's what Siegel says. And so, well, what... Probably not very well right here, but I mean, there's going to be a homotopy theory of simplicial spaces. So, and again, that actually really falls into this same type of phenomena where we're going to say if we have the category of simplicial spaces, and then we have some equivalences in that category, which are level-wise weak equivalences. And if we localize that category by these level-wise weak equivalences, we're going to again get an infinity category, but we could take the tau less than or equal to 1 of that, and that's basically what it means to have an equivalence of simplicial spaces. I mean, so if we take P, apply this realization construction, and then retake the Poincare infinity groupoid, we're going to get a simplicial space which is level where there's going to be a map. These two are adjoint functors. I mean, I guess if you set this up correctly, you're going to get an adjoint functor to that one. And the adjunction maps are going to be level-wise weak equivalences of simplicial spaces. And on the space side, the adjunction map on the space side is going to be an equivalence. So I mean so it's not. I guess after you do this for a while, you get the hang of how to make statements like that. But so it really means that. So I mean, what we're doing here might not be all that satisfactory from certain points of view, from a computational point of view, because what we're claiming here is that this notion of structure, this kind of structure is really, it's a whole collection of spaces. So we're really interested in the structure as a structure on P1, on just the loop space itself. But what Siegel says is that structure is really given by a whole collection of spaces that you have to add on in addition with their map. So I mean, they're sort of bigger spaces than the P1 you had itself. So it's not exactly a kind of structure in the algebraic sense. But I think you can kind of see here, this is an extremely flexible and nice way of looking at things. So let me just, as I'm erasing the H space, let me just point out how the multiplication shows up in this picture. Okay, so how does the multiplication show up? Composition. Composition shows up from the following diagram. We take P2, we map it to P1 cross over P0, P1, then we map it to P1. So this is by the 0, 1, and 1, 2 edges. This is by the 0, 2 edge. Okay. The Siegel condition says that this is a weak homotopy equivalence. That's the Siegel. That's condition B. So if you think of weak homotopy equivalence as being basically an invertible map of spaces, that means that we can start here, we can invert that map, and then project down to here. And that's the composition. And in a similar way, a diagram that you would write with P3 is going to sort of be the homotopy theoretical witness for associativity of this composition. And so if you think about it, you really need all of you need all of the simplicial level. And in a more quantitative sense, if you go up to a certain degree in the Positnikov tower of your spaces, you're going to need the simplicial things up to like k plus 1 or k plus 2 of that level. Okay, so Now, we can just take this as a definition. So we'll use this as our sort of second version of an infinity category. Okay. So we'll say that a Siegel category is a simplicial space. So by that, what you're supposed to read is really a bisimplicial set. So in other words, it's a function from delta op cross delta op into sets. This is not the simplex delta. This is the category delta. Let's call it A. Such that 1, we require that A0 be a discrete set. In other words, A0 comma K is constant in the second simplicial variable. And 2, just this condition B. We're not going to put condition C. Condition C would be the thing we would put if we wanted to have a Siegel groupoid rather than a Siegel category. No, so I'm going to get to that in a minute. In fact, in a Siegel space, you don't put this condition, you put a different condition on the A0. Which, I mean, so I'm presenting the whole theory from my own point of view. I mean, I think that's why you guys want me to give the talk, you might say. But anyway, or maybe you don't, but I mean, okay, you're stuck with me, okay. So I'm presenting this from my point of view, which is not necessarily the same as other people's point of view, but of course, everything converges in some way, somewhere or other. But I do think that this is, I'm kind of intuitively, it's all kind of pretty natural, right? You want a notion of path, you want a notion of loop space, and this is really like a really beautiful way of making a notion of loop space. I mean, it just works totally well right away. You don't really have to do anything, right? This simple fact that the n simplex retracts onto its spine, that tells you automatically how to make composition of paths, which if you think of just trying to concatenate paths, well, you can see why it's going to be, why multiplication is going to be associative up-to-homotopy, but if you think of trying to turn that into really a whole discussion of a mathematical structure, it doesn't seem all that obvious how to do it. I mean, I guess you can, but, or this is just sort of obviously works perfectly well. Anyway, but in this point of view, what we're doing here is we're discretizing the space on the 0 level. So, and then the second condition is the Siegel condition. So is that for all n, say, greater than or equal to 2, we have a n dot. So, this is a bisimplicial set. So it's really there's two simplicial indices. So we're writing the first one first, which is the one we're talking about here. The second index is just the index that's talking about it being a space, okay? So that's a simplicial set, but that's just saying it's a space. I don't need to put a dot for the 0 because of this condition that it's constant. So this is just a single set, whichever the simplicial index you take. So one has to be careful. I mean, if you're trying to write this down at home, you might say, okay, I'm getting confused. What are the maps? These are the maps these are the maps that are dual to the inclusions like 0, 1 into 0 and 1, 2. 2, 3, and so on. What you might call the principal edges of the simplex. So they're just dual to the inclusions of adjacent pairs inside the ordered set. Okay. The condition is just that this is a weak homotopy equivalence. I should also say that we came upon this whole picture during the thesis of my first thesis student, Zuhair Tamsamani. So, and this discussion really is in his thesis, although the main section of his thesis is about what happens when you do this, you iterate it, and then you sort of truncate at some higher power of n at some point. But to prove the thing, to prove some of the stuff in there, that's how we learned about this whole theory, basically. Okay, so that's it. That's it. So that's the Siegel category. So then there's a theorem of what's going on? So this is the notion of sorry, maybe I need to say okay, I need to how are we doing for time here? I need to say what's a morphism. So a morphism of these things is just going to be a morphism of bisimplicial sets. Now, what about truncation? So truncation. So as before, we defined the tau less than or equal to 1 of A dot is the category whose nerve is the simplicial set n maps to pi 0 of A n comma dot. Okay. That's a 1 category. Now, what's the notion of equivalence, which I think should be called Dwyer-Kahn equivalence? But it's really, we're just sort of copying the notion of equivalence of categories. So, I mean, the idea here is that this is really supposed to be thought of as a category where the A1, we're going to have A1 is going to be a disjoint union of A1 of xy. The condition that the A0 is a discrete set, that's going to make A1 into a disjoint union of A1xy. A1xy is just in a simplicial set you have a map from A1 into A0 cross A0, just given by the two face maps. And A1xy is just the inverse image of x comma y by that map. Okay. And so we would like to think of this as a spatially enriched category where the set of objects, so ob A is just A0, and more A from x to y is just A1 of xy. And the A2s, A3s, and so on, the A2 is there to make a composition operation like we did there. The A3 is there to make the associativity and so on. Okay, so put all together, we get what's a simplically enriched category-like object. Okay. Now, there's a construction which is if we had a simplicial category, if let's say B was a simplicial category, we can put an of x0 comma xn to be defined to be equal to b of x0 x1 cross b of xn minus 1 xn, and the strict composition law, the strictly associative composition law of B, gives us directly a simplicial set. Where the Siegel condition is true up to isomorphism. And actually, if you think about it, conversely, if you have a bisimplicial set, bisimplicial set. If you have a bisimplicial set such that the A0 is constant and such that the Siegel maps are isomorphisms, then that corresponds exactly to a simplicial category. Okay? So we have sort of the category of simplicial categories. Maps to the category of Siegel categories. Now, there's a notion of equivalence, which I actually didn't say for the world of simplicial categories. I guess you were asking for a review of the definition of simplicial category, but why don't we just take that as definition of the simplicial category? Okay. What's the notion of equivalence? And similarly, I'm going to define equivalences for Siegel categories, but you can just transform back. That's the notion of simplicial equivalence for simplicial categories also. So a functor, so a morphism. So now the new B is not necessarily a simplicial category, but a morphism is a Dwyer-Crown equivalence if two things hold. So now we just copy the notion of fully faithful and essentially surjective. Okay, so fully faithful what does fully faithful say for categories? So fully faithful says if you have two objects in the first category, then the space of maps from those two objects in the first category maps isomorphically to the space of maps between f of x and f of y in the second category. So I guess we need a letter here, f. Okay. But now the whole idea here, the yoga of going to higher categories, is we replace sets by spaces and replace isomorphism of set by weak equivalence of spaces. So we just do that exactly. So it says that if for all x, y in ob A, so remember that's A0, the map A of x, A1 of x, y, so that's the space of morphisms from x to y, into the map B1 of f of x, f of y, is a weak homotopy equivalence. Remembering that these are now spaces, right? Because we had a bisimplicial set, but this is the first simplicial variable, so this is a simplicial set in the second variable. Okay? And what does essentially surjective mean? It just says that the functor from tau less than or equal to 1 of A into tau less than or equal to 1 of B is essentially surjective. Or we could also just say that tau less than or equal to 0 of A surjects onto tau less than or equal to 0 B. Or we define tau less than or equal to 0 of A is just the isoclasses of tau less than or equal to 1 of A. So the point here is that to decide whether a map is defined to be an equivalence in an infinity category, you just project it to the tau less than or equal to 1 to the category, and then decide whether it's an equivalence. Okay? And well, when you work out the theory, that comes out to be the same as sort of saying invertible up to homotopy in some more complicated way. So that's an equivalence. Now, I can actually state the theorem right away, but you need some extra stuff to actually do this. But running a little late on time. The theorem. Sorry. I think this is basically due to Julia. Yeah. says that if we take the category of simplicial categories, and it would actually be a good idea, as you guys now know, to take the Dwyer-Kahn localization of the simplicial categories by this class of weak of equivalences. But we could just take the localized category by dk. So we can just take the usual localized category. So this is the Gabriel-Zisman localization. That's not mine, right? That's fine, just as long as it's not mine. The map from the Gabriel-Zisman localization, where you invert the equivalences, mapping to the same thing. This is an equivalence of categories. And the stronger statement would be that if we did the Dwyer-Kahn localization of those categories, we would get an equivalence of infinity categories also. So this is now there's sort of stronger things. So maybe I should, let's see, we're out of time here. Oh, certainly, yeah. You have to, yeah. But let's like take a growth-unique universe or 2 or 3 or something like that are embedded, and okay, what's going to happen if somebody shows that the existence of like 2 inaccessible cardinals is like contradictory or something like that? Then we'll probably have to go back and rewrite a lot of stuff. But by then, hopefully, computer theorem proving will work so well that we'll just be able to go tweak a couple things and recompile it. So. Okay, so anyway, but yeah, I mean, you do need to, but let me not do that here. So let's see. I did kind of want to finish the discussion of Friday's discussion. So maybe next time we'll get to other models. So these are 2 models for infinity categories. Okay, so these are 2. There are other models, are what's called quasi-categories, by basically Joyal and Lurie. In fact, I mean, it goes back way a long time, in fact. Boardman and Vogt. But I mean, of course, as I think many of you know very well, of course, this theory is mainly developed in Jacob Lurie's gigantic book or books, which has, I mean, that's one of the reasons why I'm sort of feeling free to not really talk too much about proofs, because the best place to go for proofs is Jacob Lurie's book. But so I would like to get to kind of try to explain at least intuitively how you get to the notion of quasi-category, at least in my point of view, starting from this direction. Yeah. That's a good question. That was the growth-unique said, we're going to have definition A, definition B, definition C, and then mathematician A wants to show that his definition is equivalent to mathematician B's definition. So there's a whole paragraph about that in Pursuing Stacks, where you don't have a conclusion, but I mean, I don't know. I mean, the whole thing, it has this kind of circularity feel to it in the sense that it's really hard to get a hold on like a total, and this is even a research question. It's really hard to get a hold on a sort of a thing which tells you what you have to do without making any choices. I mean, we've made some choices here, right? We've chosen that the Siegel thing looks like a good idea. We chose that simplicial categories look like a good idea. I mean, we chose that simplicial sets look like a good idea for spaces and so on. So I don't have an answer to that. will extraterrestrials have a sort of totally orthogonal theory to us, possibly? Anyway, but let me just list these. So like two other main models are quasi-categories and then what's called complete Siegel spaces. By Charles Resk. So complete Siegel spaces is a theory that looks a lot like this, but it's not. It's really kind of different in the sense that you're not taking this point of view that A0 is a discrete set. You're taking the point of view that A0 is something more complicated, so I'll need some time to explain what that is. But it's kind of the interior groupoid of your category. So if you have a category, you can sort of look at all the invertible submorphisms of it. That's going to be a groupoid, and then you can sort of redo Siegel's delooping construction and get a space, and that space is supposed to be A0. So that's a little bit more philosophically complex. This is actually simpler in the sense that it's just a single variable simplicial set rather than a two-variable simplicial set. And it's a simplicial set that's supposed to satisfy what's called the restricted Kahn condition, which appeared, Boardman invoked. I mean, I should say that the notion of Siegel category appeared in a paper by Vogt and appeared in papers by Dwyer and Kahn. And as I said, but I mean, I don't really see why didn't appear in a paper by Siegel, because it's just a totally trivial extension of the idea of Siegel. I said that should be just a single point, but if you just say it could be several points, I mean, it's the same. But anyway. So we'll talk about these later. But let me just finish by going back to the example of Friday. Which is that we had this category C, which was something like that. We put these two guys inside W. Then we said that if we took the localization of C, so let's call this A. Localization of C by W, let's call that A. That's basically going to have two objects X and Y. We'll sort of throw out these ones. It's going to have two objects X and Y, and A1 of XY is going to be S1. It's going to be a circle. So we kind of justified why that looked like it was probably true. Then we can also look at L of C, invert all the morphisms of C, and that's going to be B. Okay? So now the question is, what is B? So what is B1? Or since they're all invertible, it's the same thing to ask, what is B1 of XX, you might say. Well, I mean, this is not a justification, but this is just sort of a coherency check, which is that we wanted this to be sort of coherent with the notion of a functor to spaces which sends our subcategory to equivalences. So we said that a functor to spaces F from, and we kind of justified this, at least roughly speaking, that a functor to spaces from C that sends W to equivalences is really going to correspond to an action of S1. So if you think about that a little bit, you can sort of see, I mean, this is just going to, we're saying that we have two different morphisms of spaces, and this side gives a homotopy between them, and this side gives a homotopy between them. Putting those two homotopies together, it means we have a whole S1 acting on, one of these things. So this is going to be, we're going to have just basically S1, which is A of X, Y, is going to map to morphisms from Fx to Fy. That's the condition of if W goes to equivalences. But if we, in addition, ask that F of all of C goes to equivalences, then we're saying that we have a map from S1 into equivalences between Fx and Fy. Now, if you think about it, if you use this to glue, so S1 equals the equator. So you can sort of use this to glue together two copies. So you sort of glue together Fx and Fy. But we have a S1 of equivalences between f and y, fx and fy. So we have a whole S1 of ways of gluing fx to fy. And if you think about it, that really makes a fibration over the circle. Oh, sorry, over the sphere. And S2 was the nerve, the realization of the nerve of the category. Okay. So then what my slogan for the day was that a fibration over a space is going to be the same thing as a functor from this Poincare infinity groupoid of the space into spaces. Well, as I said, this is not a proof, but here we said we have a functor. I mean, but sorry, this should be the infinity category. The universal property of localization tells us that we should have a functor from that we should have a factorization. So having a map from C into spaces that sends all of the elements to equivalences is supposed to give us a map from the localization into spaces. So as I said, this is not a proof, but this is a probability argument that it looks quite likely, therefore, that this thing should be the same as that. So then the statement is that L of CC is going to be equal to pi infinity of the S2, which is pi infinity of the realization of the norm of the nerve of C. And this is a general phenomenon. If you take a category and you localize all the maps, then you get a sort of a spatially enriched category, which is the pi infinity of the nerve of C. So this tells us the answer. This B of xx is just the loop space of S2 at the point x. Okay. So that's back to that example, to some extent at least. So I'll stop here.
Any questions? So it's more a request. So in the first lecture you said that the infinity category is one to prove theorems faster than without. You showed some evidence of this in the next lecture.
I guess so, but I think some of the other talks may be slightly evidence for that. I wanted to explain what was going on as much as possible. But yeah, okay. So I think the next lecture I want to discuss these other models for infinity categories. Then I'd like to discuss what you can do with the infinity categories as a theory, basically. So.
Other questions? So here you decided to keep the first zeroth level discrete.
Yeah.
What if you kept some rounded levels?
Well, that's not. He said, what we kept the zeroth level discrete. What if we kept some other levels discrete? That actually brings us to the question, the definition of there's something called a two-Siegel space by Kaparnoff and Dikerhoff, maybe. In which case that's probably relevant. Here you can't. That's not going to work too well with this condition that says that everything is up-to-homotopy is determined by the A0 and the A1, right? Because A2 is A1 cross A1 over A0 and so on. So if A1 was discrete, then all the other ones would have to be homotopically discrete. What you could do is you could sort of try to bump up in a different direction. So you could try to look at cases where the spaces are sort of highly connected, for example, 2 connected, 3 connected, and so on. And there you would get something.